Hey, hi. Welcome back to the SystemVerilog sequence session. So I hope you already had a chance to review the introduction, which is a very important point. And as a part of the introduction session, we had seen that assertions are primarily helping us, model the behavior of a system in the form of a waves, and then we are actually capturing a waveform in a concise and complete format. And the way we captured was made up of several layers. If you remember, the lowest is Boolean expression, and then combining the Boolean expressions with the timing operators, we formed the waveform, and then we took it and then used those sequences in properties, and properties gave the validity to the timing expressions that we had created. And then the properties were combined with directives, like you could assert it to check cover, to cover a particular thing, assume for generation, and then we put it in a unit, compilation unit. It could be either a module, checker, interface, or a program block, and then we can deploy that, right? So this is what we fundamentally saw. And then we know that the properties have to be constructed using sequences, and everything that you can put in a sequence can also be put in the property. And the reason for creating this sequence construct is so that you can divide the properties into smaller timing expressions. We are forming a complex timing expressions using the smaller timing expressions, which you are putting it in the sequence. So sequence is, in a way, you can think of it like a task or a function, where you are putting in the reusable part of the code, and even you can pass the arguments to sequences, and hence the sequences can be made reusable across multiple properties. So that's the idea of sequences. And sequence have their own operators, and we will look at overall sequences in much more detail in this session. So let's get into it. So the agenda for this particular session is, it's three folded. First is that we will understand what's the scope of sequence. What does that mean is, what does it mean to learn a sequence? So we will look at that, and then we'll understand different operators that are present within the sequence. Is a very important topic again. And we look at the delay operator, which we have briefly looked, the double pound sign. And then we will understand that if if we are not using like a validation, like what we are calling, if we unguarded or non-validated sequences, when they are directly used in the property, what happens. We will look at it a little bit, and then we will take a small detour and understand this implication operator. There are different operators present in property, and we will just understand this implication operator or implication property, because without knowing this, we cannot create meaningful examples. So we will look briefly into it. Of course, the final session we will look properties in much more detail, but in this session we'll just do a small detour to understand the implication operator, and then we'll understand the repetition operator. That is, if a particular Boolean expression is repeating, how do we represent that effectively? So we'll look at that with the repetition operator. So at this point, using delay and repetition operator, you will be able to create a good number of timing waveforms, and then you can combine them. That's the second phase, right? So you are able to define one, now you combine them. You combine multiple waveforms together and say and of this, or the intersect of this, or the first match, or the sequence within. So now you are playing with multiple timing waveforms. At the first level, you are defining one waveform. At the second level, you are playing with multiple of them and putting it together and composing more complex waveforms. So that's the idea. And the third stage is, there are few operators, like we have sequence triggered, which indicates the completion, and then there are local variables. So you cannot build lot of logic, additional logic, as we have talked about, within the sequence or within the properties. And the best that you can really do is using some local variables and doing some some sort of few operations on those local variables. But beyond that, like if you want any complex modeling for supporting your assertion or a sequence, you'll have to do it outside as a part of auxiliary HDL code. And then we'll see how to call some subroutines on a match of a sequence, which is very helpful while doing the debugs. And then how we can pass arguments to sequence, as we talked about. Sequence are your reusable timing waveform. So if you want to make it reusable, obviously, like let's say I am saying repetition, so if I can send how many times do I want to see the repetition, then that is something that helps me make it reusable. So how I can pass those arguments, we will see in the passing arguments to sequence. And then there are a bunch of sample value functions, and we will see those which are those and how we can make use of it. So this is broadly the agenda, and as a part of our sequence, the SystemVerilog Assertions learning, this is going to be the slightly longer session. After this, the properties one is shorter compared to this one. That's because, as we discussed, this whatever concepts we are looking at in the context of sequence, all the operators you can directly use it within the property as well. If you are not, if the overall the check that you are doing, the waveform that you are creating is simple one, then you don't really need to again create sequence, although it's highly recommended that you create the sequence, but it's not mandatory. Okay, so how does a sequence look like? So it's on the left hand side. You say sequence is a keyword, provide an identifier, then in the parenthesis you provide a set of arguments list, and then you can do a local variable declaration. Then you create your sequence spec, right? The local variable declaration we have seen even in the context of tasks and functions, so it's kind of similar. Then you define the sequence spec, which is made up of Boolean expressions and the sequence operators to create a overall timing or a temporal expression, and then end sequence is your another keyword. So sequence is made up of series of events which are defined. Your sequence spec actually is made up of a series of events defined in the form of Boolean expression, and it could be made up of other sequences as well. The formal arguments, actually you can pass output also. Sometimes after matching a sequence, you extracted certain value and you want to pass that value back to some other sequence, some like back to the property, and the property extracts it and can pass it back to another sequence. So output is also possible, and input variables also you can pass. The local variables, again, can be created within the sequence, and this is very useful, as you will see that any property can be multi-threaded. So if you declare variables within the sequence, and when the multi-threaded nature comes into picture, the every thread will have its own variable, so that way it is very useful. And then the clock or a sampling event can be either explicitly specified. So for example, we had seen property, and within property we were saying like at passage of a clock. It need not only be clock, it can be any signal, but we were typically using at passage of clock. So we can put that within the sequence as well, or it can be implied based on where the sequence gets used. So sometimes, let's say you built a reusable sequence, and then it's getting used in different properties, and those properties, let's say, are operating on different clocks or a different sampling conditions. Then you don't want to specify a sampling condition within the sequence, because that makes it more specific. So you don't leave it out, and then depending on the context as to where the sequence gets used, it will inherit, or the clocking event gets implied, and hence the sequence becomes more reusable. And sequences again can be defined in your checker, module, interface, program, clocking blocks, packages. They can be defined at different places. See, we can define we define it in the package as well. So we will look into it as to what are the packages. So what is the scope for learning the sequence? If you look at it, then it's made up of these four components. So first is sequence operators, the delay, the double pound one, then there is a repetition operator, then there is a throughout operator that you want to check that a particular signal is asserted throughout some specific sequence. You can use that within, like you want to check something has happened within. And then there is a intersect, we will look into it. And then there is a first match when there are multiple matches possible, you want to start something on first match, you can use first match operator. This is an again an important operator. And then you have the sampled value functions. These are very useful. You have $fell, $rows, and then $stable, $change, $passed, $sampled. If you remember, we had used this $sampled in the action block to print the value sampled in the preponed region. And we will look into the usage of each of these sampled value functions. They are very useful. So typically, if you don't use the sampled value function, a particular variable used becomes level sensitive. But when you use this, like for example, especially the $fell and $rows, you can create a edge sensitive, especially when you want to use it in the antecedents. These functions are very useful. And we briefly talked about passing arguments to sequence. We'll look into it. And then local variables are very helpful concept, especially for managing the managing multi-threaded nature of execution of sequences. Because what happens is, if we define external variables, then we don't know how many times the particular property is going to get executed, right? Because we don't have any control on how many times it is going to get triggered. So if there is a local variable, what happens? Every time it gets triggered, automatically the variables within that particular sequence get created. So that way local variables are very helpful. And as we talked about, like combining sequences, you could composition, you can create or you can do and or of different sequences. So we will look into how to create more complicated sequences using the simple sequences. So that is the overall scope for learning the, when we say learning the sequences, these are the items that we need to learn to complete the sequence understanding. So let's look at the sequence operator. So let's start first with the delay operator. And the delay operator is represented by this double pound sign. So when you can say double pound and number, or double pound or number range, that specifies the delay from a current tick. Okay, whatever tick that it starts executing, it specifies from that tick how much delay are we specifying, right? And these number or the number range that we specify, they have to be constant. You can't use variables over there. Okay, and then the time window specified within the number range can be finite or infinite. I mean, finite or unbounded. So unbounded means it will come by the end of simulation. That's what you are saying by unbounded. And the way you represent unbounded is through this dollar sign. So I can say a double pound n is again a constant, can be any number, integral number, and followed by a dollar. It means, let's say if I put 10 to dollar, then after assertion of A, and from the 10th clock onwards to the end of simulation, any point of time B can come. Okay, so that's how you specify the unbounded values. And the value of n here, it can be 0 or any positive integral value. I just took an example of 10, but it can be any number. And then here I can specify a finite bound as well. So this, we have already seen this example. If I say a double pound 1:3 B, then what it means is B can come on clock 1, 2 or 3 after matching A, right? That's what it means. And what happens is, property will match on the earliest clock edge. That is, let's say B comes and B is asserted for 3 clock cycles. Okay, then what will happen is, it will not pass on the last clock cycle, it will pass on the first clock cycle. Okay, like for example, in Python, when you do regular expression, you have greedy match, that it will match at the most maximum that it can match, it will match that. But here the sequence, it's not like that. So sequence will match as soon, okay, as soon as it is seeing the B has come, the property has passed, and the further whatever the assertion of B has taken place, that will be ignored. So now these are some of the side effects. Okay, and if you think that your specification doesn't intend that if the B continues to be asserted, and that is an error condition that you have to explicitly specify again as a part of your sequence, saying that if this happens and after that after the next clock cycle, if I want B to go low, then I will say again double pound 1 and not of B. Okay, I have to do that explicitly, it's not automatic, because that is something that we might be thinking, because we generally look at, this is one challenge with assertions, that we think of a passing scenario, but we don't think of side effects, right? So that okay, whatever the scenario that we have in our mind, it will pass, but it will pass for many more cases than what we have in our mind. Okay, this is a very important point, that you have to understand this very clearly, that you have certain waveform drawn on the paper, and every time you start writing an assertion, because we have been emphasizing it again and again, it's all about waveform. So you have to draw the waveform. Okay, what are the possible cases? You have to draw it. And when you say what are the possible cases, you have to be as explicit about it, because if you cannot just, so you think about a passing case, you write it, as I said, it will pass for that, but it will pass for many more conditions. As we saw in this case, if the B continues to be asserted, it's not a problem for assertion, but if that's not the intended behavior, then there is a problem. So that you have to take into consideration. We will look a little bit more into like how we should structure our thought process, so that we have good chances of getting the assertion right, and that will help. So we will look into it, but still it's not easy. And so that, and other point that I want you to notice is, again, it's a double pound, not a single pound. Pound, sorry, we were using it for the Verilog delay, right? And then in the sequence, like a true, or like which is represented by your one tick B1, or sometimes just called tick 1 also. Okay, this don't get confused. If some places, if you see tick 1, it implies it's one tick B1, which is nothing but true, right? So implicit enables implicit success enables the sequence to progress further. So if a sequence I have defined from one stage to another stage, it progresses. For example, this sequence progresses to the checking of B only after it has found the A, right? So if I want it to progress to B without waiting for A, progress means we have to wait after, let's say I have to check at some point of time, the B should come at the beginning only after 3 clock cycles, and I don't have anything like A, I can put one tick B1 over here. So that is how the sequence will progress, and this is what we are talking about. Okay, and this is useful. We will see when we are collecting some local variables and all that, we will use this to collect the information. So just remember this point. Okay, let's look at some of the examples of the delay, sequence operator delay. So we have this pound 0 A, which means on the same clock cycle. Okay, whatever the point, this expression executes on the same clocking event. If A is true, then this expression gets satisfied. This timing expression gets satisfied. These are all timing expressions. These are not the Boolean expressions anymore, because this is a delay operator, is a timing operator. So now if I say double pound 1 A, it means that one clock tick later, and it implicitly takes that before this there is one tick true. That is, it assumes that A was true, or like the sequence was true, and it progresses, and then after one clock tick it checks for the A, and if it finds it true, then this double pound 1 A timing expression gets satisfied. Similarly, if it is double pound 2, it skips 2 clock cycles, and on third clock cycle, if A is true, then this expression is satisfied. And if it is double pound, and if I'm using the range operator, then what that means is, since I'm using 0 over here, on the immediate clock cycle where this is getting used, if that is true, then it is satisfied. Or if it is comes out after one clock, that is tick true, and double pound 1 A, which is similar to this one, if that happens, it is satisfying. Similarly, this double pound 2 and A, then it is satisfying. And then if it is triple, like the double pound 3 will be like true, and then delay of 1 true, delay of 1 true, delay of 1, and then even if the A shows up after 4 clock cycle, this particular expression will be satisfied. So immediately to first, to second, third, or on the 4th clock cycle, if A shows up, then in all those conditions this particular timing expression will be satisfied. And then of course you can do n, we can put any integral value over here, and then on the nth clock cycle, after nth clock cycle, if A is sampled and is found to be true, then A pound n b, of course this n has to be a constant integral value, and that will be satisfied. So in next few slides, what I want to show you is how to apply the thought process that we talked about, right? In the previous slide, we looked at that there are cases where it could pass for more than for the different possibilities than what we are targeting, and it could fail for different possibilities than what we are targeting. So how do we identify them? How do we come up with them? So I will show you, and also show you why it is important. That is also equally important to understand, that unless I show you some surprising cases, then you would say that, yeah, Anand is making me do extra work. So you will think like that. It's not like that. I'll show you a few examples why we have to be more careful. So let's take a simple sequence. So we have this sequence S request grant, and what we are doing over here is we say request, and both the request and grant are level over here. So as soon as, and because of this level usage, also the number of cases become more. Okay, so to prevent that, we can also use sampled functions. So usage of sampled functions makes it more specific. So I think you should definitely consider looking into it. But let's start with how generally we would do, and then evolve to that. And that also helps you understand that, you know, what could be the potential issues, right? Because every time you may not be the one who is writing assertion, someone could have written assertion and you have to debug a failure. At that point of time, you don't have the control, so you have to understand what exists. So let's start with this. So we are saying as soon as the request is asserted, level is what we are looking for, request is asserted, then on the third clock cycle, the grant must be asserted. That is, after 2 clock cycles, which is third clock cycle, the grant is asserted, then this timing expression will be satisfied. And I am using this sequence in this property p underscore request underscore grant, and I am triggering this property on the passage of clock. So now note that in the sequence I have not specified any sampling event, but the based on the context that is in this property, since I'm using the sequence S request grant in the context of at passage of clock, it will automatically this sequence will also be triggered on the it will be sampled on the passage of clock. So that happens automatically. Then we are saying end property, and these are the labels. So highly recommend you that you use the labels, and sometimes a property could be a much bigger property. So a label, if it is more than a page worth of code, then the label becomes easy to identify where it's beginning and end. And then as we have seen that just declaring the sequence and properties doesn't enable it in the simulation, we have to combine it with one of the directives to enable it. Here we are doing assert, and this label is even more important than this label, right? So here, unless you put this one, when it fails, the name can be some auto-generated name from the simulator, and that can be very confusing. So I say assert property p request grant, and if it passes, I'm going to say it has passed, and I'm going to display some time and values. And then if it is an error, then I say failed, and then I display time and some values of some signals, right? So that is what I'm going to do. And now when I have such a property in front of me, what should be my thought process, right? So I have to ask myself, when does the assertion start? Okay, so now I know that it's on every passage of clock, because there is no antecedent, right? So we have seen antecedent and consequent type of a format based on implication operator, and here, as we are not using any implication operator, on every passage of clock, this particular property is going to get evaluated. Okay, so the next question that I need to ask is, when does this end? Okay, so as we have already seen, on a passage of clock, when the grant is observed after 2 clocks of request assertion, one thread of the property will end. That is when that is going to end. So we have to ask these 2 questions: when does it start, when does it end, right? And then when does it start becomes even more important, because when you use an antecedent, then the antecedent condition must be satisfied. Okay, so that you have to take care. Now the next condition is, what are the different pass criteria for this particular property. Okay, now we might imagine a waveform that is there in our mind, that okay, the request gets asserted for 1 clock, then the 2 clocks no activity is happening, on the third clock grant is asserted, and we think, yeah, that is a ideal case where this particular property will pass. But in this case you will be surprised that the request, if I never want this property to fail, then request must be asserted, right? And the first time grant gets asserted after 2 clock cycles, but thereon both the request and the grant must be asserted all the time for this property to pass, right? Otherwise, if at any point of time that condition is not satisfied, it will fail. Okay, don't worry if you are not able to visualize this waveform, I will show you further. Then all fail criteria is any clock request is not asserted, because there is no guarding condition. See, this is the value that a property construct brings in. Okay, property construct has the implication operator through which it can build, through which it can bring in a guard condition to determine when this validity of this timing expression begins, right? Without that, what will happen is a sequence by default is expected that its first Boolean expression must be true on any clock cycle, right? So on any clock cycle, if request is not asserted, this particular property will fail. Okay, and any clock request is asserted and grant does not show up at 2 clocks, after 2 clocks, right? Then also the property will fail. Okay, and then we have briefly looked at sort of hidden meaning, how the assertion operates. If we don't understand it properly, it looks hidden. So if assertion is waiting for a grant, and within those 2 clock cycles, if the request gets asserted again, another thread of this particular property gets launched. That is one hidden aspect of it. And second hidden aspect of it is, if it gets launched, then as soon as the grant comes, for one grant, let's say I have 2 requests, but one grant is coming in, both the threads will get satisfied. So this is one hidden aspect of it that you have to understand very clearly, otherwise it will remain hidden. So, but this concept of hidden, you have to keep it in the back of your mind, and hence whenever you see a property, these are the questions that you should practice thinking about, that when this assertion is going to start, when is this assertion going to end, what are the like all pass criteria, when under what all conditions it is going to truly pass, and what will be the different conditions in which it is going to fail. And this hidden is that I am calling it hidden, although you understand it, but it may not be obvious that the thread getting launched, unless you practice it again and again, thinking on those lines, it won't become your second nature. So it will be hidden for some time, right? So you can think of it as like a blind spots while driving the car, right? So this is the one, like the threads getting launched is one blind spot of assertions. So you have to consciously practice it for a while till you get used to it. Okay, let's look at some of the examples to understand what do we mean by these hidden cases very well. So since this is the first example that we are looking closely, I want to just set some like the precedence of how the information will be displayed in different waveforms that we are going to see. So what I have done is I have added the assertion itself in the wave window. This is the Questa simulator. The similar capabilities would exist in all the industry standard simulators. So I added the assertion, and if you remember, we had given the name a request grant, and I have expanded that assertion, and then that will show me the signals used in the assertion. So I can see clock, request, and grant. And I have added one additional variable called count in all my assertion examples, so that it becomes easy for me to count or to refer when we are discussing about a clock edge, because sometimes this the timestamps at the bottom may not be very clear. So I've added this count for counting as well as referring. Now let's start looking into it. So what this is showing is it is showing me where the assertions are failed. Wherever we have the red dots, the assertion has failed. And wherever this green line, continuous line appears, this line indicates that assertion was active during this point. Okay, that's what it indicates. and then we have the clock, we have request, we have grant. Now let's understand why assertion has failed over here on this particular clock where the count is 0 on this edge. Why assertion has failed? Can you think about it? So here it has failed because request is not asserted, right? Since the request is not asserted, this assertion has failed over here. And why has it failed on the clock edge 1? Although the request is asserted over here, why has it failed? This has failed because if you remember, the values of the signal are sampled in the preponed region. So this request has been asserted on the rising edge of the clock, but on its preponed region just before the clock event, the value was still 0. So this assertion has failed on the count equal to 1. But on the value of count equal to 2 on this particular clock edge, this request is detected and hence the assertion has become active. Okay, it's tracking now. So now what it is going to track, let's look at it. So it is tracking, and on the count where it is becoming 3. So here our assertion is we are saying it is request pound to grant, and we know that pound to grant means tick true, pound 1, tick true, pound 1, and followed by grant. So that twice it has to be true. Okay, so on this clock edge the request is true, on the edge where the count is 2, and on the edge where the count is 3 the request is true, right? It is still true. Okay, and after that grant has shown up, right? So after 2 clock cycle, the request being true, the grant has shown up. So this is one endpoint for the assertion. So we would have expected the assertion to complete over here, right? But it has not completed. It is still continuing to progress further. And why is that happening? That is happening because of threads. So at this point one thread is launched, and at this point another thread is launched. Okay, and this thread that is launched at 2 will expect 2 clock cycles. So it is going to expect 1 and 2. So it's going to go up to that point, right? And the one that is launched over here on the count equal to 2, it will again wait for 2 clock cycle to determine, and this is going to go from 5th to 6th, right? So it is active till that point. Okay, so that's the whole idea, and each one of them it's launching the threads. So a thread is launched on count 2 and the thread is launched on count 3, and the one that is launched on 3 was supposed to it will go up to 5, right? And the one that's launched on the 4 will go up to 6, because the one that we launched on 2 went up to 4, right? Because we have double pound 2. So that's why it has gone up to 6. Okay, so this is the indication through which we can understand that the threads are being launched. Now there is a second point that we should understand at the clock edge 5. Okay, assertion, if I look into the log files, it's not going to be visible in the waves, but if I look closely in the log files, I have put the action block, and in the action block we had put $error, and that is showing up twice at this 55,000 picosecond or 55 nanosecond. It is showing up twice. Now why is this error message showing up twice, right? So we have to understand that. The first reason being that at this point, okay, at the point where the count is 5 on this clock edge, the request is not asserted. So since the request is not asserted, the assertion has failed. And another one is because the request was asserted on the clock cycle where the count was equal to 3, and for that one, after 2 clock cycles we were expecting the grant on the clock edge of 5, and that grant has not shown up, right? So because of that as well, the assertion has failed. So there are 2 threads of assertions that were active and both of them have failed. The same thing will happen even at the clock edge 6. So if we look into the logs, it would fail twice, because the one that was active on the 4, it's not showing up at the 6, and as well at the 6 the request is not asserted, so it's going to fail twice. So this also confirms the fact that we had the multi-threaded execution, and you can understand that by looking at the behavior, that how long the assertion was active and as well as how many times the assertion is failing. And I would encourage you guys to experiment and see so that you can convince yourself better on this particular case. And this is a very important concept, that how the assertion gets attempted, how the threads get launched, and how they pass, fail, and how they end. So this is a very important concept. Okay, we'll look at one more interesting example. So I have again added the assertion over here, and on this clock edge it has failed because request is not asserted. On this clock edge it has failed. Although the request is asserted, it has failed because in the preponed region the request was not asserted. And on this clock edge the assertion has started, right? It has started, and which is the equal to the count 8. This particular assertion has started, and then on the count when it becomes equal to a, there is a grant showing up, and hence I am expecting that at this particular timestamp, that is 105 000 PS or 105 NS, I am expecting the assertion to pass. But if I see, I can see this red dot over here, the assertion has failed. But if I look closely in the log, the assertion has passed at this 105, and also the assertion has failed. So at the same clock edge, which is the clock edge corresponding to count of A or this 105 nanosecond, assertion has both passed and failed. Okay, now why it has failed? Okay, the reason why it has failed is because request is not asserted. Okay, because its request is not asserted, it has failed. But and why it has passed? Because of this assertion thread that we had started on the at the point where the count was equal to 8, right? On this clock edge, because of this request, the thread that we had started has passed at this point where the count has become equal to a, and since the grant is coming in, so that has passed, that thread has passed, the new thread that's launched here has failed. So that is why we see a pass and fail happening at the same time. So we saw in the previous one 2 failures on the same clock edge, and here we saw like there is one pass and there's one fail. Okay, so this. So you need to keep this in mind. So when you are debugging assertions, you should be alert to take a look into log as well, because it provides you a lot of valuable information. And you have to combine log and waveforms, because assertions are waveforms. They are concisely capturing waveforms. Of course you need waveform, but waveform alone are not sufficient. You should look into the logs as well, and for that you should have put the appropriate information in the action block. And what you need to take care is, initially you can put both the pass and fail, but eventually you should eliminate the pass part of the assertion, because it might pass many times during the course of simulation, and it might end up cluttering your log file. So that you have to take care. While your initial debug part, you might want to put it and check it, and after that you just keep the else clause. Okay, here we will take a look at scenario wherein what if we do, the assertion will keep on passing. So we'll look into that. So again we have added the assertion. It has failed on this particular clock edge because the request was not asserted, and after that the request has been asserted, and at this point the assertion has become active. And after that what we are doing is, from this clock onwards, right, we are keeping the grant high all the time. That will keep the threads satisfied. So on every clock the request is asserted, a thread gets launched, and after every 2 clock cycles from this point onwards, right, it will expect, like for example this clock edges thread, okay, this will end over here, but whereas this clock edge, it will expect the grant to be asserted after 2 clock cycles. So on and so forth, it will continue. So for this is the waveform where they keep asserted all the time is when the assertion passes, and this may not be evident when you take a look at the request followed by pound to grant. You might not have thought that this is the waveform which is what you are really capturing. This may not be evident. So that is also because of level sensitive nature that we have used and plus we are not using any implication operator, like validity for the sequence expression, and hence this is what it ends up with. So this is a point, you should make sure that you have understood this clearly. Okay, so the pound delay operator that we have seen already, it's also a sort of concatenation operator. It can be thought of like a concatenation operator. And so far in all our examples, we were seeing only one level, but you can use it as many number of times, right? And you can create an indefinite chain of events you can define using the this double pound operator. And if in these cases, like if you want an overlapping type of an operation, then you can also use pound zero, right? We have already seen that if it's a non-overlapping, you use a value of n greater than 0. For overlapping, you use pound zero, which means a and b happening at the same time, and this above is also equivalent to a and b. Okay, so you can do a and b and same as that, that is both of them are happening at the same time, and then only it will go further. Hey, we saw the usage of sequence within the property without any guard, and this type of usage without validity doesn't have much of a practical use cases, especially for assert. There are some use cases when you use it with cover directive, but with the assert or assume type of directives, this way of utilizing a sequence directly within the property without any guard is not very useful, because when you do this, what happens is it expects the trigger or the condition to be met on every clock cycle, and then it can lead to false failures. And most of the practical use cases have some sort of trigger to indicate the start of sequence, and only after the sequence trigger is detected, you need to check whether the rest of sequence is taking place. And without the guard, what will happen is that the sequence is expected to start on every clock cycle, which is not going to happen in real scenarios. For example, an AXI transaction, right, will not start on every clock cycle. It takes some time to complete a particular transaction and then start the next transaction or next phase of the transaction. Now we cannot put an restriction that the transaction must start on every sampling event unless and until it's a part of specification. So we need a guard condition to write useful properties which can be used in the assert. Okay, so for the reasons that sequence directly when used in the property doesn't yield meaningful results when we use it with assert, what we will do is we'll briefly take a small detour and learn a bit about property. And I know we have seen briefly, and we will mainly look at how the implication operator of property works. Okay, and then we'll come back to the sequence operators and learn all the sequence operators. And the idea is this way we will be able to showcase more meaningful examples of how to build sequences which are eventually used to compose the properties. And once we complete that, later in the third session about SystemVerilog assertions, we will revisit the property construct in detail. So property is a construct that captures the behavior of a system, and it can natively define the behavior using various operators that we have discussed. And for about the sequence, like for example the delay operator can directly be used in the property, and also all the operators that we are going to discuss in the context of sequence can also be used in the context of property. And then the property has its own operators, and the primary function of those operators is to act like a precondition to filter out either inappropriate or extraneous situations that can happen in the sequence. So they provide some sort of validity to the sequence that we are using, and then how long a particular sequence needs to be active or when is it going to become active. All that can be controlled using the operators provided by the property. And it's note that it's highly recommended that you build properties using the sequences, because it makes understanding properties easier. But as we already have, we are going to see that the properties are really tricky and they are hard to understand. So if you build a very complex property in one place, then it's going to be very hard to understand. So if you break it up into smaller sequences and you give a meaningful name to the sequences and then you compose a property using them, then it's much more easier for understanding, maintaining, and then debugging, and also the sequence can be reused. And as we have been emphasizing this point again and again, just declaring property doesn't affect any simulation behavior unless you combine that with one of the directive is when it really gets enabled in the simulation. That is your assert, cover, or assume. You need to add it to the property in order for the property to get enabled. And properties can be declared in module, interface, clocking block, program, package. I think they can be declared in any of these constructs that are provided by SystemVerilog. There are 7 different ways to build the properties, and we will look at each one of them when we go to the property construct. So the first one is a sequence, where you just directly use a sequence without any property operators. I think this is the one that we already saw, that we defined a sequence and we directly used it without any guard conditions which are based on property operators. So that's a sequence type of a property. And there is another property, and this type of property is built using either the other properties. So you can compose properties of properties. So you have defined a property, you can use that particular property in another property to build more complex properties. Like you can use a sequence within a sequence, you can also use a property within a property. That is also possible. Or there is also a recursion that is supported in the property. You can use that. And there is an inverse where you have either a property or a sequence and you negate it, saying that okay, if like request followed by grant, you can negate it. Or like, you know, if something supposed to be a Boolean expression is true, then you can negate it and check for the false. Then there is a disjunction, which is or of 2 properties or the sequence expression. And then there's a conjunction, which is and of 2 properties or the sequence expression. I think the term disjunction conjunction is used to differentiate between your typical and or. And then there is a if else type of a conditional evaluation of property or a sequence expression based on Boolean expression is possible, wherein within a property, let's say you could have defined another timing behavior using different properties and or using sequences. Now based on certain condition, you can invoke different timing expression to be checked. So that is possible. So that is something that you can do it with the if else. And then there is the last, which is the implication property. So the implication property is the one that we are interested in, because that's the typical use case. So this is a behavior, this is a way to define a conditional behavior. Now the question might come in our mind that what is the difference between an if else versus an implication. So if else provides the way to specify like a conditional expression, conditional timing expressions using a Boolean expression. So it's based on a Boolean expression. Okay, so when you say if, you have to put a Boolean expression in that, but you cannot put a sequence like saying if this particular sequence and then you do something. That's not possible. So if you want to do that, that is something that you do it with the implication operator. So in the implication operator, you can say if this particular sequence is satisfied, or if a particular sequence that is specified using a property itself is satisfied as a condition. So in a condition, in implication, you can use either a sequence or you can use another property. But whereas when you do the if else type of a property definition, you can use only Boolean expression. You cannot use another sequence or a property in the condition of if else. So we will look little bit more deeper into the implication property first, so that as we called out, we want to use it in the different examples of the sequences. So in the implication operator, the check on the property is performed conditionally on a match of a sequential antecedent. So we have already seen the sequence expression on the left side of your implication operator is called antecedent, and the one on the right side of your implication operator is called consequent, right? So when the antecedent is completely matched, that is the endpoint of match of an antecedent sequence expression is actually the starting point for the evaluation of your property expression. Okay, so there are two types of implication operators. There's one which is called overlapping, and notice the way like you have a pipe minus and followed by greater than sign. So this is your overlapping. So here what happens is the endpoint match of antecedent expression is the start of consequent expression. It's the same clock. Okay, so for example, we had taken the let's say we have a request and we want to check, followed by that, like as soon as request is asserted, let's say we want to check the grant, right? We want to use the overlapping operator, and the same sampling event, as soon as the sequence expression is satisfied, you want the property expression to start matching, right? So the endpoint of your antecedent expression is the start of your consequent expression. That's what happens in the case of overlapping. And in case of non-overlapping, which is represented by pipe, and instead of minus sign now you have equal to, and then you have a greater than. So this is the non-overlapping. And in the non-overlapping, what happens is you expect that after the endpoint match of your antecedent expression, the start of consequent expression start one clock later, right? That's what happens in case of non-overlapping. As the word is saying, non-overlapping, right? So on the clock event where your antecedent has matched, like I can say request, and then if I use an overlapping operator, it expects the grant to come one clock next clock, right? Not on the same clock where the request has matched, but on the next clock. So that's what is the non-overlapping. And you can represent the non-overlapping using a overlapping implication operator. I mean, it's kind of equivalent. You can say #1, #1, tick true here being like the define that we had defined. It's like one tick P1 or tick 1, and then I can use an overlapping operator and say the property expression. And so this is the sequence expression #1 tick true, that is one clock is passed, and then you can use the overlapping operator. So it's equivalent to this is the equivalent representation of non-overlapping using the overlapping operator, which makes it more clearer. So in the implication operator, right, on every successful match of your antecedent sequence expression, which is on your LHS, a separate thread is launched which tracks and evaluates the consequent property expression, which is your right hand side. Now, because of this, there can be multiple threads that can be active, and you need to keep this in mind because multi-threaded assertion can sometimes lead to a very confusing results. That is, an assertion could appear to pass and fail at the same clock cycles. That's because an previously launched thread could be seeing that a particular consequent matching its endpoint at a particular given clock edge, and it could be passing. At the same time, another thread could be seeing an violation and it could be failing. Okay, so this is very much possible, and this is something that we need to keep it in mind. And second thing is that with respect to multiple threads, it can so happen that multiple threads are launched when the your antecedent criteria is met, but same consequent matching can lead to termination of all of them, and sometimes you want it and sometimes you do not want it. Like for example, this request followed by an overlapping 1 to 3 grant, if the request appears 2 clock cycle back to back, then there are 2 threads that are getting launched. And what can happen is that eventually on, let's say, a second clock cycle grant comes in, then both the threads will get satisfied. So the thread wouldn't care that for which one the consequent expression is getting satisfied. As long as the consequent satisfies both the threads, then both of them will terminate. So this is something that you need to keep it in mind, that this condition can occur While when you use the implication operator, because you are guarding, still the results will be more, less likely to face a false failure type of a conditions. But without implication operator, the threading can have a lot of side effects. There is another term that you will come across when you are using the especially the unbounded delay range. It's called vacuous pass. So what happens is when we take an implication property, let's take this is a non-overlapping. So we have a request followed by a non-overlapping implication operator, and it's saying $1 grant, that we are expecting the grant to show up by the end of tests current test simulation. Okay, and here the I'm just repeating, the antecedent is your request and consequent is grant. Now it can so happen that even when the end of simulation is reached, that the grant may never come. Okay, now since like let's say the antecedent is met, that is a request has come but a grant never showed up, the property could still show that it is pass, and it's called as like a pass vacuously at the end of sim. Okay, the simulators could show this. Now vacuous means that emptied or lacking of content. It's a root in the word vacuum, right, in the air, what we call in the slang. Now there are two ways you can address this issue. So there is an operator provided called strong. So you can make the your consequent strong, so that you can say like request this non-overlapping implication operator, and you say strong of consequent, and then what will happen is that the simulator will not give you a vacuous pass on this type of properties. Or you can disable the vacuous pass using your assert vacuous pass as well. This vacuous pass actually affects when you are doing coverage, because it could appear that it is falsely covered. Okay, so if you are using it for coverage, then you want to take care that your coverage is not because of an vacuous pass where antecedent is satisfied but a consequent is not satisfied, and because of that you are seeing a property as pass, and that pass is leading to coverage bins being hit. So you don't want that to happen. So in such cases you want to use strong and make sure that it is not showing a false coverage. But by default this consequent has a weak type of a match requirement. We will see what is a strong versus weak in a bit more detail in future, but just keep this point in mind that when you have an unbounded range, that it can happen that a property might show as a pass but it has not really passed, and leading to false coverages. So at this point, I think we are ending the detour that we took, where we discussed a bit about property and especially the implication operator, and we saw why the implication operator was important, so that we can validate the sequence as to when it should happen, without which the property would expect the sequence to hold true on every clock cycle, or expected to trigger on every clock cycle, which is not how the most of the real life use cases work. And when we do that, it can lead to a lot of false failures. So we have looked at it, and now we have all the bits and pieces needed to look more deeper into the sequence operator. So now what we will do as a next step is we will learn all about different operators and how to all aspects about the sequence, and then we'll go back to the different types of properties and to learn more about properties in the next session. So from the next slide onwards, we will get into how the sequence operators work. So we have already looked at a delay operator, which was double pound and could be followed by a integral number or a range of numbers. Now we will look at the second one. This is a repetition operator, right? You remember that we have been emphasizing that the assertions are a way to concisely and completely capture a waveform or a timing relationship made up of different Boolean expression, right? And part of waveforms is a repetition. Now the repetition can be some signal or condition that's being asserted for multiple clock cycles back to back, that it is staying true, or it's valid for a multiple clock cycle, or it is some signal or condition repeating in a form of pattern every few clock cycles, right? Like you can imagine that we have a circuit that generates a pulse every 10 clock cycles. Okay, so now that is a repeating pattern. Okay, or I could have an enable signal which is holding true for 4 clock cycles back to back, right? So that's a signal that is asserted multiple clock cycles, so it is a repeated pattern for us. Now when we have such a repetition in the waveform, the sequence, this repetition operator can be used to capture that repetition. Now there are three kinds of repetition operators that are provided. The first one is called consecutive repetition operator, and it uses this star followed by either a constant or a range expression. So that's how we represent the consecutive repetition. And what happens is when you use the consecutive repetition operator, the expression must hold on successive clocks for the repetition count or the range that you have specified. So it has to hold on a successive clock. So it's back to back, it has to hold. It cannot go low if you are checking for true. So that's what it means for the consecutive, right? As the name itself also suggests. And then you have a non-consecutive repetition, which is represented by this equal to, and then like of course the square bracket and then equal to, and then you provide either a constant or a range expression the way we have used it with the delay operator. Here the difference compared to consecutive repetition is that expression must hold for specified count or a range, but it need not be on a successive clock edges, right? So if I am putting a repetition for 4 clock cycles on a particular signal, now it could be asserted for 1 clock cycle at one point, then it can go low, again go high, but essentially it happens 4 times. That's what we are looking when we are looking for a non-consecutive. It need not be on a back-to-back clock cycles. And the third one is slightly tricky to understand. When we probably look at an example, it will become more clear. It's a go to repetition, and what it means is go to a repetition followed by a particular expression. Okay, there is one more expression that follows, and it is a non-consecutive. It's a special form of a non-consecutive repetition. It says a non-consecutive repetition with a condition. Okay, then you specify an additional condition post your non-consecutive repetition, and that condition, whenever it is satisfied, I want to go to that particular non-consecutive repetition. Okay, so I know this may not be very clear at this point. I think when we look at the example, it will become more clear. But at this point, just understand the fact that there are 3 types of repetition operators. You have consecutive repetition, non-consecutive repetition, and go to repetition. Consecutive, non-consecutive are very clear. The go to repetition, just remember that it's a special case of non-consecutive with an additional condition attached. At this point, just remember that, and when we go to example, we'll look at it in more detail. Okay, we'll take a look at example for the repetition operator. So let's start with the requirement. The requirement is that we have a trigger signal that triggers the sequence, and along with the trigger we have another signal called start that gets asserted, and 1 clock after the start gets asserted, we want a signal called enable to get asserted and stay high for 4 consecutive clock cycles, and then it should go low. This is our requirement. Now so now we have multiple ways. We have 2 ways in which we can implement. So first, look at if we are not using any consecutive repetition operator, how would we implement this? So here we are defining a sequence. So yes, trigger pulse simple. We are saying start, and after start 1 clock later enable gets asserted, and then we have 1, 2, 3, 4, right? Each of them separated by 1 clock delay with a double pound 1, and then double pound 1 because we are explicitly saying that the enable should go low. Then we are making sure that we are deasserting the enable. Okay, so we are doing this, and this is the sequence that we have created. and we will use the trigger for as an antecedent to qualify this particular sequence, and then we are creating the property. The property is triggered on at the passage of clock we are using as a sampling event. It can be any other signal as well, and we are using the trigger to qualify the start, and then we are using a non-overlapping because we indicated that the trigger and the start needs to come on the same clock. So we are using a non-overlapping implication operator, and we are calling the sequence that we have defined. Okay, so now this is a good enough, I mean, this is going to work to meet our requirement. Of course, if this were to be 10 clock cycles or 127 clock cycle for something specific, then of course this code would have become very long. So the way we can represent this repetition more concisely is using this repetition operator. So if we rewrite this simple sequence using the repetition operator, it will look something like this. So I'm defining a sequence with the sequence keyword s trigger pulse repeat. Then I have the start, I look for a start, then one sampling event worth of delay or 1 clock worth of delay. Then I'm saying enable, and in the square bracket with the star I am putting the count 4. Okay, so what this means is that this is in fact equivalent to this enable pound 1, enable pound 1, enable double pound 1 enable, right? 4 of these what we have seen over here. This enable hash 4 is equivalent to this. Okay, so it is going to check that the enable remains asserted, not check, I should say, it represents, that is very important, because I don't know whether the property is going to be used for coverage or whether it is going to be used for check. So I cannot say that. So all I can say is that it represents the enable being asserted for 4 consecutive clock cycles. That is what the enable square bracket star 4 and the closure of square bracket means. And then I will say this double pound 1 delay operator, and then I'll say not of enable. That part remains same. Okay, and then the rest of the property usage remains same. So at the passage of clock, I'll use the trigger and I'll use the non-overlapping implication operator and call the sequence that I have defined with the repetition. Now let's look in the waves as to how it behaves. Again, we have added the assertion. I am not shown this property being called with a directive. So it's called, the name of the property with the directive is a trigger pulse repetition, and then all these signals are showing up over there. Now if we look at the waves, then when the count is equal to 1, both the trigger and the start are being asserted over here. Now immediately on the next clock edge, the enable gets asserted, and it remains true for this count equal to 2, 3, 4 and 5, right? So 4 clock cycles it's remaining true, and then at the count of value of 6, the enable signal is going low, and at this point where the count has become equal to 7 on this particular sampling event, when it samples the enable being low, that is this point, is when the overall property is satisfied, and hence you see that this the active duration of this particular property has ended. It has started as soon as the antecedent has been satisfied, and it has ended when the endpoint of consequent, the endpoint of consequent is the not of enable. So when the endpoint of consequent has been satisfied, the property has completed, or property has ended, or it's satisfied, and at that point the property has passed. Now here we are using a simple Boolean expression, right? So we have used enable, and in the square bracket star 4, which represents the 4 consecutive cycle assertion of our enable signal. But it need not only be like a simple a Boolean expression, it can be a sequence as well. So for example, I could be saying a delay operator with the 2 clocks, 2 sampling events with B, and this is a sequence. So now I can put a repetition on this particular sequence. So what this means is it expands to something like this. So then a delay operator of 2 clock cycle, B followed by 1 more clock cycle, then on the subsequent clock also it should hold, and on subsequent clock also it should hold. Now 3 times there should be a repetition of this particular sequence. So this particular sequence means A gets asserted, and then 2 sampling events later the B gets asserted. This type of sequence happening 3 times consecutively. Okay, so that is when this particular sequence will get satisfied. So the repetition operator can also be used with the sequence. So we can for example, this entire sequence that we have, wherein we have the start followed by enable being asserted and enable going low, we can say this has to be repeated, okay, 4 times, right, or 2 times after every start. That also is possible. So here for this S trigger pulse repeat, I can put again a square bracket and put 2, then the 2 times. Now at this point we again expect the start to come in, enable to hold true for 4 clock cycle, and then again go low for 1 clock cycle. So that repetition has to happen consecutively immediately at the end of this, the next one starting, and then the property will be satisfied. So you can use the repetition operator with the sequence as well as with the Boolean expressions. Okay, let's look at an example for the repetition operator with the non-consecutive repetition. We are taking again the similar example. So if I am replacing in the sequence, instead of consecutive repetition, I am replacing here with the non-consecutive repetition. So the non-consecutive repetition is with equal to 4. Okay, and then I am saying a not of enable. Then at the triggering edge of pause edge of clock, if the trigger shows up, which is your antecedent, then with the overlapping operator I am expecting this particular sequence which has a non-consecutive repetition to hold. Okay, so let's look at the waveform. Now if we see over here, okay, what's happening is we are getting a trigger on this count equal to 1, and the start is also asserted immediately. Now if you see, the enable has been asserted for 1 clock going low, asserted for 1 more clock is going low. So this has happened for four clock cycles, and then it has gone low at this point of time, and that's when the entire property is satisfied and it has passed. So you can see the active duration. So as soon as the antecedent has met, it has started, and then it is waiting for this 4 clock cycle up to the count of 9, and after the 9 it is going low, and that is satisfying the not of enable on a count of A, where the count becomes A, this particular clock edge that is satisfied, and hence this particular property has passed. Now one point to note over here is that when you are using a non-consecutive operator, repetition operator, even if this was asserted 4 clock cycles consecutively, still the assertion would pass. So that is something, because consecutive is a subset of non-consecutive, so even then it would pass. So that is something that you need to keep it in mind. Okay, let's take a look at go to repetition example. As I had talked about, it is a slightly confusing type of an operator, and it's hard to understand unless we compare it with the non-consecutive, because as we talked about, it's a special case of non-consecutive. So let's do that. Okay, so here we are creating an example. So we have start and then followed by enable. I'm using a non-consecutive repetition operator for enable, and after 1 clock delay, we are expecting the done to be asserted. So that is a sequence for which we are looking for, and then at the passage of clock we wait for the trigger, and then we are checking whether the S trigger, the non consecutive repetition sequence holds. Okay, so this is the way we have done the non-consecutive repetition, and this is the exactly same sequence, and the only change over here is I have replaced it with the go to repetition. Okay, so just I hope this is clear. So we say start, and then we say go to non-repetition or the go to repetition, and then say done, and so this is repetition go to, and then this is repetition non-consecutive. So the names are indicative. And now let's look at the waveform. Okay, so pay attention over here. Now what has happened? So is the we have had a trigger which starts the sequence, and then immediately in the same clock cycle we expected the start, because at the both the places we are using the non-overlapping implication operator. So it is at the same point, and then enable has toggled for the 4 clock cycles. Enabled has toggled for the 4 clock cycles. So in both of these we have given the same stimulus, okay, and we are observing the behavior of non-consecutive repetition versus the go to repetition. Okay, so the top one is your non-consecutive and the bottom one is the go to repetition. So in both of them same. So we have given it for 4 clock cycles, and after that we have the enable being deasserted for about 3 clock cycles. So being on A, B, and on the C, and then we have the done coming in, right? So after 2 clock cycles, right, the done is coming. So the enable is deasserted, and after deassertion, after 2 clock cycles, the done is coming in. So we have 1, 2, and actually 3. After 3 clock cycles, the done is coming in. Now when the done comes, the your repetition non-consecutive has passed. Okay, so I can see that it got activated as soon as your antecedent condition was met, and then as soon as the done, which is the endpoint for your consequent, because this is the our sequence is the consequent. So as soon as the done came, the sequence got completed. Okay, so this has passed successfully. Whereas if we look at our go to repetition, it has failed. It has failed as soon as we have had the 4 non-consecutive repetition of enable. So we reached this point. So we had the start, we had a non-consecutive repetition 4, which completed at this point, and at this point it was expecting, actually it completed at this point, right at the count of 8, right on this particular clock edge it completed, and this is the 8, so it completed at this point. Now it was expecting done to come here. Okay, so non-consecutive assertion passed, it would have passed if the done had come over here. Okay, done, if it had showed up at the point where it is failing, then the go to repetition would have passed. Okay, the non-consecutive repetition operator doesn't care when the done comes. As soon as it comes, it will pass. Whereas go to repetition expects that this last condition that we have mentioned after the go to repetition must be met in the successive clock. If it meets, then only the go to repetition will pass, otherwise it will fail. So that is a difference between your non-consecutive repetition versus the go to repetition. Now let's look at a passing condition. So here what we have done is we have provided a waveform where the go to repetition has passed at the top, and the bottom waveform is same one as we had seen in the previous slide. I just kept it for the sake of comparison, quick comparison. So here we are again applying the waveform to both the assertions, that is your non-consecutive repetition as well as the go to repetition. So we at this point the assertion, both of the assertions have started because the antecedent condition has met. We have had a trigger as well as the start coming in, and then we have had a 4 non-consecutive enable signal assertions, 1, 2, 3, and 4, and after that immediately following that clock cycle we have seen the done. And in this case both the assertions are passed, because the go to repetition has the mandate that the last condition must hold immediately after the go to repetition has matched, whereas your your non-consecutive repetition doesn't have any such constraint. So even if it comes over here it is fine, even if it comes after n number of clock cycle it is still fine. Okay, for that is the difference between your non-consecutive versus go to repetition. In this slide, we will summarize all the repetition types, and I think this is something that you want to make a note of it to remember. So enable in the square bracket star 4, this is the consecutive repetition. And idea is we need to look at things from different point of view. The same information, and look at it from different point of view, it consolidates and it becomes clear. Especially for assertions, it's very important. And as I've been we have been discussing, you should take these individual examples, generate different type of waveforms that you are seeing, and convince yourself. That is very important. Okay, so this repetition 4 is equivalent to enable, then delayed by 1, enable, delayed by 1, enable, delayed by 1, enable. There's a 4 times, and this has to happen on 4 consecutive clock cycles. So this is what it means. So enable star, it's not a unique thing. Okay, it can be done using the delay operator. It's just a variation of the delay operator, and only thing that it is really contributing, it makes it easy and in a simple way you can represent, but it is nothing unique. You can realize all the types of repetition using the delay operator itself. This is a point that I want you to keep it in mind, because sometimes this type of a question may come that, okay, how do you realize repetition operator using the delay operator? Then you should be able to apply this concept. Then here pay more closer attention between your go-to repetition versus the non-consecutive repetition. So if I say go-to repetition of 4, of course we need this additional condition, because that's where the difference comes in. So when you say go-to repetition, what happens is on the last clock cycle, this should hold here. So the enable, whatever the condition that we have put, that should hold over here. On the last match it should hold. That is what is the expectation. So this not of enable repetition 0 colon, we are saying unbounded. So it means any number of clocks the enable could be deasserted. After that, like 1 clock cycle delay, the enable must assert, and it should end, this last match for the enable should end with enable being asserted. So 4 times if I repeat, so imagine like this is 0, and then it goes 1, and then it can again go 0. Okay, and then again it goes 1. Like that 4 times it can happen, but the last again the enable should be asserted. Whereas when I say non-consecutive repetition, instead of go to, this was a go to repetition where the last it expects it to be asserted, whereas in the go to repetition, it is, you can see that it could be unasserted, or it could be 0, and then it goes 1, and then it can again remain it can remain 0 for any number of clock cycles. It could be 0 as well. So as you can see, this could be 0. If it is a 0, then it's equivalent to your go to repetition, but this is present. So it can be it can be that after the condition is met, it can remain 0 for any number of clock cycles, and it will still be a valid match for non-consecutive repetition, whereas for the go to repetition it has to hold on the last match. So that is the difference that we see when when we use the go to repetition. And then there are a few more abbreviations, there are short forms. So in the square bracket, if I just put star without any number or the repetition, then it is equivalent to star and then 0 colon dollar. So this, the short form of this is just star. So sometimes if you just see this, don't get confused. And then in the square bracket, if I just put plus without any number or range, it's a unbounded. So note over here that it is 1 to dollar. So if I put it 1, the plus, then it is 1 to dollar. That means that at least one time it should get asserted. Then, but if I put it star, then it is 0 to dollar. That even the 0 it will still match. For the repetition, it will still match. So just keep this thought in mind. And here the question might come, what does the repetition operator with a 0 mean? It's just an empty sequence. So let's look at it. So let's say if I have B, 1 clock delay, A, and my range is repetition of 0 colon 1 and followed by 2 clocks delay, and C. So I can expand this to B with 1 clock delay, and then the A is non-existence for the first time because the value of 0 is being used, so there is nothing. So I just have one more delay, and then I have C, then OR, then I'll expand it for 1. So I'll say B 1 clock delay, then A has now come in because it's no longer an empty sequence, and then I have 2 clocks worth of delay and C, and this one I can again further simplify that there's nothing between these two, so it's a 2 clock delay, so it's a B followed by 2 clocks delay followed by C, or B followed by 1 clock delay followed by A followed by 2 clocks delay and C. So this is what an empty sequence would expand to. So make sure that these points you make a note of it, and that will provide you the clarity. And then if you have to ever realize the any of the sequences using only delay operator, it will come in handy, as well as it brings in the additional clarity. Okay, now that we have looked at both the delay and repetition operator, now let's look at some of the sequence composition operators. So the sequence composition operators, you will use it to combine multiple sequences. Of course, with delay operator is also a concatenation, but we will look at more complex operators over here. So how you can combine different sequences. So AND is another operation that you can do. So let's say if I have, and the way it works is, if I have a sequence expression 1 and then AND, and then if I have a sequence expression 2, what this means is the start of both of these sequences should match. So when I say AND, then start of sequence for both of them should match, and then both of the sequences must complete, but they need not complete on the same time, but they must complete. Okay, that is an important point. And then whenever any one of them, like whenever the last one completes, that's the end time for this ANDed sequence. Okay, so now I hope that is clear. So if I say sequence expression 1 and sequence expression 2, both the sequences must start at the same time, both the sequences must match for the property to complete successfully, but the end time is the end time of the sequence that completes last. So this is what it means when I do sequence expression 1 and with the sequence expression 2. So let's take an example. So let's say we have a sequence S add pipe, and here I am saying AP1 1 clock worth of delay, AP2, and this is the ending. And then we have a mult pipe. Yes, mult pipe is another sequence where I'm saying MP1 followed by MP2 followed by MP3, and then I am doing the composition of these two. I am saying at the passage of clock, if there is a trigger, then I'm using non-overlapping implication operator, and I'm saying yes add pipe and yes mult pipe. So this is what I am trying to do. And now let's look at the waves to understand how this works. So here I have the waves, and here I have this our composite instruction property, which is AND of add and multiply. And let's understand. So here we have the clock and we have a trigger. Okay, so the trigger has come in at the count of 1, and at the same point we have the AP1 asserting. Okay, so our add property is AP1 1 clock delay followed by AP2. So the AP1 is asserted over here, and then immediately following that AP2 is asserting. But if you see, the mult pipe sequence isn't starting at all. Okay, so only the add pipe sequence is starting, and hence since it did not see the mult pipe starting, the overall AND property has failed. Okay, since both of them did not start, the other one didn't start at all, it has failed. Now here we have mult starting, but starting a clock delayed. Okay, it's kind of same, but it is starting here. Here it was not at all starting, it was here it is starting, but it is starting 1 clock late. So still the AND of these two is failing over here. And in the third case, if you look at it, this AP1 is coming in over here, and then followed by that 1 clock delay. AP2 is the sequence, and that has completed over here, and then the MP1 is coming in, which is your mult pipe sequence is coming in at the same point as your add pipe sequence. So it's starting at exactly at the same point, and then MP1 followed by 1 clock delay, MP2 followed by 1 clock delay, MP3. So all three of them have showed up, and note that both the sequences have matched. Okay, so the first sequence has matched over here at the clock of F, and then the second one has matching at 1 0, the count of 1 0, and only after the second sequence has matched successfully is when the property has completed, and here it has completed successfully. It started as soon as the first match, okay, and then it completed at the point where the last match took place. Okay, so this is how this works. Okay, so one correction I would like to do: it started as soon as we saw the trigger. So it's not the match, actually it's a trigger, because as we know, the implication operator, as soon as we see the trigger, which is your antecedent, the property has started, and at this point, if either AP1 or MP1 had not showed up, it would have failed, and after that it ends when the last property matches, right? And both of them have to match, both of them have to start, but it completes when the last one, last match is achieved. So this is how the sequence and operation works. Yeah, so okay, let's look at intersect operator. So the intersect operator is usage is something like this. You say sequence expression 1 intersect sequence expression 2. This is the usage, and the expectation are the start of both the sequence is expected to happen at the same time, and both the intersected, or as many sequences have been intersected, they must match. All of them must match in order for the property to complete successfully, and then both the sequences must end at the same time as well. And this is the main difference compared to the AND operation. So in the AND operation, they were both expected to start at the same time, as well as both of them were expected to match, but the end time restriction was not there, whereas in the intersect, the end time is also expected to match. So let's take a look at example. So we have one add pipe sequence where we say there is a AP1 signal, and we say that in within 1 to after AP1 signal assertion, within 1 to 3 clock cycles we should see AP2 assertions in order for the S add pipe sequence to complete. And then we have S mult pipe sequence wherein we need to see MP1 assertion followed by 1 clock cycle, MP2 assertion, and followed by 1 more clock cycle, MP3 assertion for the mult pipe sequence to complete. And we have a trigger. Then we are writing a property. A property is sampled at the passage of clock, and the trigger is the antecedent, and then we are using the overlapping implication operator. So as soon as trigger is asserted on the same clock event, we expect the S add pipe to intersect with the S mult pipe sequence. Okay, now let's look in the waveform how these behave. Okay, let's understand the waveforms for the intersect. So we have added the property in the waves, and here comes the first trigger at the count of 0, and in the overlapping fashion we have the AP1 assertion, and then on the same clock cycle we have the MP1 assertion. So both the add and the mult sequences are starting in a overlapping fashion along with the trigger at the same sampling event, and hence the our composite property has gotten activated. And on the count of 1 the AP2 shows up, and hence the our add sequence completes, whereas the mult sequence is still continuing, and it completes when the count becomes equal to 2, when MP3 asserted is followed by MP2 followed by MP1. So at this point it is completing, but it is failing at this point, because although both the sequence add and the mult sequence started on the same sampling event, they didn't complete on the same sampling event, so it has failed over here. Now let's look at a second attempt. We have trigger on this count equal to 6, and the AP1 is asserted in a overlapping fashion at the same point of time. But if we see, the assertion has failed immediately, and that is because the MP1 has showed up 1 clock later. So although we can see the end points of both the assertions are aligning, but the start point aren't aligning, and hence the assertion has failed immediately. Okay. The third use case, or the third stimulus, we see that trigger has come in at the count of D, and in a overlapping fashion we have AP1 assertion, and overlapping fashion we have MP1 assertion, which means both the add and mult sequence have started at the same sampling event, and then on the count of F the AP2 has showed up, which satisfies the add sequence, and because we have 1 to 3 clock delays, and then we have MP1 followed by MP2 followed by MP3, and that MP3 happens to be the end point for the mult sequence, and the AP2 happens to be the end point for the add sequence, and both of them are coming on the same sampling event. Hence both the start point as well as end points are taking place in the same sampling event for this particular property. Start point is at the same at the count of D, and the end point is the same at the count of hex 10, and hence this intersect property has passed, and this is the duration during which it was active. So let's look at the first match operation. This is again a little tricky one to understand, so pay attention. So, and this first match is useful when we are using the in the antecedent, right? We are using a sequence, and a sequence containing a range, okay, the range of delays. So whenever you are using an antecedent that contains a sequence, and that sequence contains range of delays, is when the first match is useful. So you have to understand that use case. But let's define what is the first match operator. So first match operator matches the first of possibly multiple matches. So what does this mean? Multiple matches of an operand sequence, we'll look at it, and then subsequent matches are discarded. Okay, so this effect will be this effect becomes clear or becomes useful when you have the antecedent, which is a sequence, and it also contains range. Okay, and why is that? Because when you use a range, okay, it creates multiple threads, and what are those we will see with the example, and each triggering the matching of a consequent. So that creates, so for the range, when you put the range of delays, for each of the value of the range, a thread gets created, and it will start looking for the matching of consequent, and then all the threads must hold for the assertion to pass, the complete assertion to pass. And because now that might not have been your intent, it can lead to two things. One is sometimes it can lead to unexpected errors, and then second is there can be a performance impact, and both of them can be avoided using the first match. So let's understand. Let's take an example. So what we are interested in is that we want, when the start rises, so here we are using a $rows function, so which means that there is a 0 to 1 transition. We have not studied the sampled value functions, but just take it on a face value over here. We will see this function formal definition soon towards the end of this presentation. So we are using a $row start, when that means that instead of level we are now looking at an edge, that is a 0 to 1 transition, and followed by that within 2 to 8 clock cycles we want to see ready. So this is the sequence. Now this sequence is nothing new, but what is new over here is that this sequence, typically we have used it in the consequent so far in all our examples, but in this case we are using this sequence as a part of your antecedent. So here when I am writing the property, I am saying at passage of clock, whenever this particular sequence, which is an antecedent, is satisfied in a non-overlapping way, I want to check whether done is asserted. That is on the next clock cycle. After matching this sequence, I want to check whether done gets asserted. This is what is now my requirement. And like our go-to repetition operator, first match also will not be clear unless and until we see something in action without first match. So when we do something without first match and when we do something with first match, then it will become clear. So we have two properties using the same sequence. The one is not using the first match, another is using the first match. It's exactly same, and it says first match of this particular sequence, and then we want to say done. Okay, now how these two properties will behave differently, we will look at it. So what is our expectation? Our expectation is when ready comes within 2 to 8 clock cycles, we want to, and any of them, it could be on second, it could be on third, or it could be on eighth, whenever that happens. Okay, I want to check whether done comes following in the next clock cycles. That is all that my requirement is. Now, but when I write it without first match, we will see what happens. So this $rows start, followed by this range of delay and ready is equivalent to, we have seen this is equivalent to rows of start and followed by 2 ready, or it could be like here it's a OR of sequence, then $rows start 3 ready, so on and so forth up to 8. So it's a OR of all of them. And when it is OR, and if it was used as a consequent, the behavior would have been just a simple OR. Okay, so if I had reversed it, let's say a trigger, and then I had said a non-implication, non-overlapping implication operator and followed by this sequence. If the sequence was on the right hand side, then it would just have been OR of these. What it meant was that it would have still launched threads. Okay, but if any one of the thread got satisfied, anyone, okay, it's satisfied, the overall property will end and the remaining threads will get discarded. That is what will happen when it was using in the consequent. It was still launching multiple threads, but any one of them satisfied, it was discarding the rest. But the same range based sequence, when it is used in the antecedent, the behavior becomes slightly different. So this OR part remains same, but with this OR now we have an additional implication. So if I expand it, what will happen is it will become $rows start, then 2 clock delay ready, and then with the implication it will become done. And now what will happen is, because of this implication operator, it will be and then with 3 ready done, and so on with 8 ready done. So now it's a and of all these 7 threads. Now all of them have to pass in order for the property to pass. That is how it has changed, and that is not what was our intent. Now we will see whether in the waveforms is this behavior visible. Okay, so let's look at the waveform. So here we have the waveform. In this first waveform, this is using without first match, and this waveform is also using without first match. So we will understand the behavior clearly, using without first match. Without using the first match operator. Let's understand the behavior. So in this first case, what we have done is we have asserted the start, and there is a $rows we were looking at, and $rows start. So at this point we have seen the event that it has gone from 0 to 1, the change is detected, and hence the property has become active. Okay, so it has remained active. Now this is remaining active for all your 7 clock cycles. Okay, it is remaining, it has started at 2 and it is up to your end of 9. So it is remaining active for 7 clock cycles, which are indicative of your 7 threads. And it is not showing any failure. Although ready is not coming in, it is not showing any failure because it's a part of antecedent. It is still waiting, and all those 7 threads will vacuously hold true, and hence property is satisfied vacuously at this point of time. This is what is happening. Okay, but in the second waveform, what's happening is that at this point of time the ready is coming in. Okay, on the count of 6 the ready has come in, but we are not still getting done. Okay, the done has not been asserted. Okay, only the ready has come in, but the done is not asserted. And since it was expecting that immediately after this ready, like a non-overlapping, it was expecting done. So at this clock cycle where the count equal to 8, the assertion has failed. Okay, since it has not showed up, it has failed, and then it has completed. Okay, so now what we are able to see over here is that if the antecedent was not fully satisfied, then we could see that all the threads are getting launched. So that is a point that we need to keep in mind, and those threads will continue till a point where the assertion fails. Otherwise it will continue to remain active. Now let's look at when the assertion passes for a specific point, what happens to those threads. Now in this case we are showing without first match and with first match. Okay, there both of them are there, and in the top waveform what's happening is same. So we have seeing the start, and at that point these both the assertions are starting off. Okay, and then at this point of time where the count equal to 6, the ready comes up, and immediately on the next clock cycle we are seeing the done as well. But as soon as done comes, okay, if you see the behavior of the first match, then the property is satisfied and it has completed. Okay, whereas for the case where we are not using the first match, it still continues. Okay, it continues, and only after all the 7 threads duration, all the 7 threads have completed, then only the property is completing, and these remaining threads are extra simulation resources. And if it is a much longer delay, let's say 100, 127, then so many threads will unnecessarily keep waiting, and they will all slow down your simulator. If you have multiple instances of this particular assertion, let's say we have even 32 instances of this particular assertions with 127 or 128 clocks waiting, then you can imagine the total number of threads that would be outstanding, and they would unnecessarily keep running, and they can cause unexpected errors as well. For example, if ready got asserted for an additional clock cycle, sometimes they could cause failure, which might be unintended in some cases. But whereas when we use the first match, as soon as the match is found, the remaining threads are discarded, and then the assertion progresses further. So in summary, whenever you have an antecedent which is a sequence, and that sequence contains a range of delays, then you have to remember that with the implication operator, of course whenever we say antecedent, it implies there is an implication operator. Then you have multiple threads, and if you and then what you are really interested in is the only one, when the first one really matches, you want to progress further with the matching of the consequent, and the remaining threads you really want to discard them, then you can use the first match operator, and that is that will save you a lot of debug effort as well as the simulation resources. We have seen that assertions are nothing but waveforms, and waveforms are created by your design, and various times we have design having certain patterns that needs to be checked, and one such popular pattern is that certain expression or like certain sequence of events are valid only when certain another signal or expression holds or true. Okay, so like for example, in an AXI interface, valid must be asserted on all legal data transfer. So I could figure out like for example, what's the total count of data that needs to be transferred based on the width of the bus, data bus, and then the total length that needs to be transferred, and then the width. Now I know how many clock cycles the data enable needs to be asserted. So that is something that we can assert, and unless the valid is asserted, then we cannot consider that as a valid transfer, right? Or the reverse might also be true, that certain sequence must not occur when certain other signal or expression is true. So this is a very frequently used requirement, and such requirement, there is a shorthand that has been created called throughout. Okay, and what the way it's used is some expression or signal throughout a sequence of expression. So now what this means is this sequence of expression must occur, or when this occurs, this expression must hold true throughout the interval of this particular sequence. Then only the overall property is satisfied. So that is what the throughout operation means, and it's a abbreviation for your expression with like a conjugative repetition operator from 0 to $, intersecting with your sequence. So that is what the abbreviation for the throughout operator means. Now let's look at one of the waveform to understand this further. So here we have our sequence. The sequence is as soon as the error flag. The requirement is something like this. So when the error gets asserted, okay, when the error is asserted, we would like the error flag should set in next clock tick, and it should remain set throughout the duration of 3 clock ticks, where interrupt should be asserted and ready should be 0. Okay, so what we want is we want the error signal to assert, and as soon as error signal gets asserted, we want the error flag to get set, and that should remain set okay, throughout the duration for 3 clock cycles, where the our interrupt and ready are in this state. That is, interrupt should be 1 and ready should be 0. So this is the condition that we are this is the sequence that we are checking. So the way we have modeled it is, let's start from the property this time. So we are saying rows of error, that is we are seeing a pulse on error, that is 0 to 1 transition, and when that happens, we are in our consequent we are calling this sequence, and in this sequence what we are saying is the error flag must remain set throughout this sequence. So what is the sequence? So we want the interrupt to be 1 and ready to be 0 for 3 consecutive clock cycles. Okay, during this sequence the error flag must remain set. That is what we are trying to check, or through the assert, or it could be cover as well. Generally I am using term assert, but it could be cover as well, or assume as well. So we can use different directives. We will look at directives more closely when we look at the properties. So let's see. So in this waveform we have added this assertion, and we have all the signals present, and if we look at over here, we have the error coming in. So we have the error pulsing over here, and that means the $rows of error has been detected on this particular clock cycle, which is at count 3, and then error flag is set. Okay, and we have 1 clock delay over here. So we are seeing that 1 clock delay, and after that we are seeing the interrupt is asserted for 1, 2 and 3 clock cycles, and during which the ready is low. Okay, so we are looking for ready is low, and this is the sequence, right? The sequence is interrupt being 1 and ready being 0 for 3 consecutive clock cycles is the sequence, and throughout this sequence the error flag is holding up. Okay, and hence this particular assertion passes. So that's the usage for the throughout. Okay, we'll look at within operator, the sequence operator. So the usage is something like this. You say sequence within sequence 2. I mean, if you look at it logically, I mean, the understanding would probably be evolving that in the duration of sequence 2, the sequence must happen, and it's a abbreviation for, if I expand this using the delay operators, it would look something like this. So you have a consecutive repetition of 1 true followed by double pound 1 clock delay, a sequence 1 happens, and then like 1 clock later again you have the true. So in this overall duration, the sequence holds, and there is this sequence 1 happening as a part of this overall sequence that we have defined, and this one intersects with the sequence 2, and intersect, as you know, that the start point and the match points of both the sequence should be at the same point, and since this can continue with the $, it's unbounded. It shows that it will the start and the end points will definitely match, and if we formally define it, what it means is that the start point of sequence 1, right, should be no earlier than the start point of sequence 2. If it is earlier, then it won't be a part of it, correct? And the match point of sequence 1 shall be no later than the match point of sequence 2. Even if that happens, then sequence 1 is stretching beyond sequence 2. So in either cases,
it won't be within the sequence 2, so the property will not hold good. So in essence, the sequence 2 matches along with the interval of sequence 1 and the sub interval of it, right? And on a consecutive clock cycles, whatever the sequence 1 that we have defined, it has to match during a sub interval of your sequence 2, then the composition will hold. Let's look at an example. So we have two sequences over here. One, we have this mult instruction sequence, and very simple, say it has this mult start signal assertion, level assertion, followed by double pound 6 clock or the sampling event delay, and then mult end should be asserted, and that's what is the sequence. And then we have a ALU use sequence where we say ALU start, double pound 1 ALU end, and what we are doing is that we are creating a property within property, and we are using the mult start as a trigger. Whenever the mult start is triggered, we want to check that the ALU usage is within the mult instruction sequence. So that is what we want to check, and that is what we want to assert. So let's see in the waveform to understand it better. So we have mult start over here at the clock count of 3, and then we have mult end at the clock count of 9. So we have about 6 clocks between them, and that's the total duration of your mult start and mult endpoint matching. And then at somewhere here at the the count of 6 on this particular clock edge, the ALU start is getting triggered, and then ALU end immediately on the subsequent clock, the ALU end is getting asserted. So the short arrow is the duration of ALU start or the ALU use sequence, whereas this long arrow is the duration of mult instruction. And as you can see, this is within this, the start point is later than the start point, and the match point is before the match point of the other sequence. So this sequence, ALU use sequence, is within the mult instruction sequence, and hence this particular property holds and ends at this point. So that is how the within operator works. Okay, the dot triggered is another property of sequence that can be used it can be used to indicate end of sequence. So you will be seeing dot triggered for the event as well. So it's sort of on the similar lines, not exactly same. So triggered allows us to find out the end of sequence, okay, and this can be used as a part of another sequence. Now the question that might come to us is that, like, how is it different from concatenation, right? So I can use, like, if I have a sequence, I can concat that sequence with another sequence, and thus I will know when that sequence ends, right? And that is when the next sequence is going to start. But compared to that, what happens is that the triggered allows you to identify the end of a particular sequence without consideration to the start of sequence. So if you use concatenation, then even the start of the sequence that you are trying to the concatenated sequences start and end both gets included. So of course you will detect the end, but the start will be the start of the concatenated sequence, right? But whereas when you use sequence.triggered, then it will tell you when a particular sequence has ended, and it may so happen that there are two sequences that are running parallel, and you just want to synchronize at the point a particular sequence ends, right, at the middle of some other sequence, and you want to check whether this particular sequence has ended without consideration to the fact that when it has started. Okay, so at that point you can use the usage is that you can say whatever the sequence dot triggered, and the result of operation will be either true or false. And it is true when the end of the sequence that is mentioned on the left hand side of the dot has completed. And this can be useful in two ways. One is that you can synchronize a part of a sequence to end of another sequence, or you can use the end of sequence as an antecedent to another sequence. Okay, so end of this sequence triggers with the implication operator another sequence, and as we know that they can be multi-threaded sequences. So if you have multi-threaded sequences, there can be multiple endpoints. So dot triggered will give you all of those endpoints, and if you only care about the first one, then you can use the first match operator on the sequence dot triggered to use only the first one and discard the rest of the thread. So that is possible. So you can combine that. Let's take a look at example. So here we have the waveforms. So what we will do is we will compare the concatenation with the trigger to get a better understanding. We have here an address phase sequence, and this sequence, if you look at it, we have used explicit clocking event over here. In most of the sequences we were inheriting the clocking event from the property, but here we have used explicit clocking event, and we are saying address start and followed by 4 clock worth of delay, then the address end must get asserted, and then we have a data phase where the data phase start signal gets asserted, and then after 1 clock or a 1 sampling event the data end must get asserted. Now I can write like let's say two properties, a particular property in two ways. One is, let's say I use a concatenation and I first wait for the address start to see whether the transaction has begun, and then I use a overlapping implication operator, and then I use S address phase sequence, and then say 1 clock later the data phase must start and complete. Okay, so this is what I'm doing when I'm using the concatenation, and here also the data phase will get checked after the address phase ends, but the start of the address phase and the endpoint both get included as a property, as a part of this property. For this property to match, now the start and end are included in the overall composition. But let's say if I do not want that, then what I can do is I can use triggered. So I will, instead of using the address start, I will say address phase dot triggered as my antecedent, and then I will say the that implies in a non-overlapping way the data phase must follow that. So this is what I'm going to do, and let's see how if we apply the same stimulus, how both of these behave. So here I have the property that I have added, and if we look at the waveforms, then we see that we have the address phase start over here, and that's happening at the clock 3, and then we have address phase end that's happening at the clock 7, the count of 7, that's about 4 clocks, and then immediately on the next clock cycle we have a data phase start and the data phase end. Okay, so this is what we are seeing, and if we look at the duration of the first property that we have built it with the concatenation, as soon as the rows of start gets matched, that's your starting point, and at the end of your address, the data phase end is when the overall property match is happening, or it's completing. Whereas when we look at where we are using the dot triggered, right, it starts at the point where this address phase sequence has completed. Okay, so the address phase sequence has completed on this clock 7, where the count is 7, and that's where the property that we are using dot triggered is starting. So you can see over here it is starting, and as soon as the data phase end sequence is detected, or the endpoint has reached, the assertion has completed and it is holding. So this is the difference, that how it behaves if you are using concatenated sequence versus the dot triggered, and dot triggered allows you to detect the end of a sequence and use that as a part of, either you can use that as an antecedent, or you can use as a part of another sequence to synchronize to another parallelly running sequence for which you just care about the end of that particular sequence and not the whole sequence. So you can use the triggered for that. So far we have looked at using the signals as a part of assertions, and those signals were typically some of the interface signals that we looked at, or the signals of some microarchitecture. But we can use the we can also use the variables that are present within the container of assertion. Like we can put assertions or sequences, the sequence and properties inside the like it can be in a module or a checker or a program block, right? It can be in an interface. So when we put the properties or the sequences within the containers, we can declare additional variables within that container, and those variables also can be used because the scope, there is a visibility of those variables within the your properties or the sequences, so they are visible. Now the question is that when that form of variable declaration is possible, and let's say that for implementing your sequence or properties you need some additional variables. Let's say you want to count some events, or you want to collect some data. Let's say you are implementing like a serial to parallel conversion, and then the converted data you want to check for a certain value. And now where should you be allocating, or where should you be declaring the storage for those variables which are used within your sequence or properties, right? That is a question. Now you have two options. One, you can declare them within the container, that you can declare them. Let's say you are using it within the interface, you can declare the variables within the interface and use it. Or you can declare local variables which are within the sequence. So we are discussing currently in the context of sequence, but local variables can be declared within the property as well as within the sequence. And as we know, anything that we can do within a sequence, we can do it within the property as well. So property is like a super set of your sequence. It can do more. So local variables can be declared within the sequence or as well as within the property. Now the question arises as to how these local variables are different from if I am declaring some external variables. So, or which one am I supposed to use? That's the question that will come in our mind. So local variables, as we called out, they are declared within the property or sequences. And when we use externally defined variables, externally meaning whatever the container where you are declaring the sequences, if you have declared the variables over there, then the challenge that you will see is that, as we have seen, the assertions can have like assertion by domain. I interchangeably use it for properties. So when you have the properties can have like a overlapping or a multi-threaded behavior, right? And the threads that get launched, they cannot communicate with each other. So any storage that you have allocated externally, if it has to be used by the threads, there is no way like a one thread to say, hey, I am using it, so you don't use it, or like this one I want to use it, you use the other value. There is no way to communicate such information very clearly. Okay, and there is no way we can and if there are common variables and if we are unaware of it, then you would end up overwriting the values. That one instance of your assertion thread could overwrite the value of another thread, and thereby causing sometimes false failures, right? So, and even if, I mean, it's not impossible, so you can still declare external variables and manage the multi-threaded assertion execution, but you will always have this confusion as to when to allocate, and then how much do you need to allocate, when exactly do you need to release. So all that headache will be yours to take care. So instead of that, when you use the local variables, what happens is those local variables gets dynamically created whenever the instance of the thread instance of the assertions are launched, and to whatever extent they are required, they are allocated, and they get released as the end of sequence is reached. So so whenever you have a local storage requirement to implement some checks, I think it's always advisable to use the local variables instead of using the externally defined variables. However, both the possibilities exist. So and as long as if you think you can manage it, you can still use the externally defined variables. But generally, the locally defined variables are much simpler in terms of that you don't have to worry about when to allocate, how much to allocate, when to release. So that headache is not there if you use local variables. Okay, so there are some properties for this local variables. So these the local variables are like your automatic variables in the task. They're similar to that. So you cannot hierarchically access these local variables, so it's not possible. And then it cannot be accessed outside the sequence where it is declared. That means that you have a sequence has a local variable. So sequences local variables cannot be accessed by properties, and they can be assigned using a comma separated list with the other expressions within your sequence or properties. We will look at how to initialize and how to use them in the next example. So local variables that you create, they get initialized in the observed region, and they get initialized from the corresponding ticks preponed region values. Okay, so if you are using any signals on the RHS, they get initialized from the values from the preponed region. Now, local variables have two primary use cases. So you can use for the deserialization of data, and you can use it for the overlapping sequences, like as we saw that we had multiple requests coming in while you're waiting for a grant and you want to match the count. Those type of problems you can solve it using the local variables, like either a count or a tag based matching is involved, out of order processing is there. So for those you can use local variables. And as we had noted at the beginning of this session, all the features, like all means many features of assertion, they come with a star at the top. That means that conditions apply. So even for the local variables, there are many rules and exceptions that are associated. For more information, you should refer to LRM. We are of course not going to discuss all those exceptions and rules as a part of this discussion, because there are many of them and very detailed. Okay, they are driven by use cases. So not everything you need to know. You need to know when you are using it for certain use cases. So these are something we call it as like reference material that you discover and learn on the need basis. So here, when such a the rules or the exceptions are sort of violated when you do the local variable based implementation, just remember that you can, at that point you should build an external auxiliary logic. The idea is local variables are in a way to implement a logic within your sequences, and the ability to do that is limited. So if for simple things it is very useful, but when things get very complicated, then your local variables may not hold up, and at that point you will have to go rely on the external auxiliary logic. So let's look at one of the examples. Of course, here I'm showing you a simple example, not the one where the rules and everything get violated. So let's look at it. So here is one usage of local variable. Our requirement is something like this. So we have a data buffer, and there is some data that gets loaded into the buffer, and then from 1 to 10 clock cycles after it gets loaded, the same data comes out, and we want to check that when it comes out of the buffer from 1 to 10 clock cycles after loading, whether the data that we had sent into the buffer and the data coming out of the buffer, are they matching or not. We want to check that. Okay, so that is our requirement. Now how do we go about implementing it? Let's understand. So we have a property data buffer, and we have declared a local data variable of 8 bits, and then our sampling event is at the passage of clock, and then we are saying at we are saying rows of load, that's our antecedent condition. And at this point, as we had seen that local variables are initialized with the comma separated list, so I am putting this parenthesis and then putting a comma and then saying local data variable value is equal to din, and this din is the value that it has sampled from the preponed region when the antecedent is met. And then I am using an non-overlapping implication operator, and I am saying that at that point it has to check whether this sequence holds. and to this sequence you can see that I am passing the local data variable that I had captured as an argument. And so here I have this sequence SDOut check, and I am passing the value of the data variable that I had captured. And in this sequence what I am doing, 1 tick B1, and I am putting range of delays. So it means that between 1 to 10 clock events from the point that this sequence gets triggered, we are expecting the valid to get asserted, and along with that the data out signal, the value should match with whatever I have captured with the local data variable. So the local data variable was captured when the load was performed from 1 to 10 clock cycle before this point, and then that is what we are checking over here. So if we look at the waveforms, so on the clock count of 0, we have the assertion of load, and this value 78 gets sampled in the preponed region at this particular point, and that gets captured in this local data variable. Then when the count becomes 4, now it could come at any point, but between the 10 clock cycles, so at count becomes 4, we are seeing the valid coming out. This is the valid. We are reaching the end point, and at this point, on this clock edge of where the value of count is 4, we will perform the check on whether this sequence holds by checking that valid is asserted, and the D out, which is this particular signal, this is also 78, and the value we had captured is also 78. As both of them match, the property passes. So as you can see, the active duration of the property, and there is no red tick mark which indicates that the property has passed. So this way you can use the local variables that you have declared within your property, and then you can pass it to your sequence. You can declare it within the sequence as well, and then use them for performing checks which you are doing later, and also for any serialization type of activity. Basically the idea is you capture it at one point of time and then use it at the later point of time. If you have such requirement, then you can use the local variables.
Okay, we'll look at one more example of local variables. Let's say we want to measure the period of clock and check that it is within certain tolerance range of certain frequency. How do we do that? Okay, so that's what we are trying to do over here. What we have done is we have written a property, and since this property could be attached to any clock, we are not specifying the sampling event within the property. So we are specifying at the point where we are doing the assert, so we can specify the sampling event over there. Now we are defining the property P clock period, and we are passing the clock period that needs to be checked as an argument. So we had seen that we could pass arguments to sequence, and here we are seeing that we can pass arguments to properties, and passing arguments make them more reusable, right? So here I am not passing the sampling clock, and I'm passing the period, and thereby the property is much more reusable because I can attach it to any clock, and I can pass the period of the clock that I am attaching, and this property can check that. And so let's look at what happens. So I have declared one local variable of the type time and saying current time, and if you remember, this tick 1 means it's equal to 1 tick B1, so is equivalent of that, it means true. And because the sequence cannot progress unless and until it is true, so we have put a tick 1 tick B1 true over here. And then what our intention is that on every the sampling event, which is going to be the passage of clock, we are going to be capturing the current time. So current time is equal to $real time. $real time is your system function that's going to give you the current simulation time, and the data type will be real or the time, both are same. Then we are using a non-overlapping implication operator, which means the next clock tick, which is next passage, and there we are checking whether the clock period, okay, the real time, the current simulation time minus the current time that we had captured, we are using some tolerance. This tolerance also we can pass it as an argument, is greater than or equal to clock period, and then with some tolerance it is less than or equal to clock period. So it's with some tolerance we are checking
whether that it is in the range of the clock period that has been passed. Okay, this way we can check whether the clock period is within the range using the concept of local variables. Sequences allow calling a subroutine on their match. We can call either a task or a void functions that don't return anything, and any of the system tasks we can call at the end of the match of a sequence. And this concept is very useful. Sometimes if you want to do any additional behavioral checks, you can do it in those subroutines. And even for the debug, they are especially useful because as we had seen, the local variables, we cannot access them hierarchically, but we can pass it to the subroutines, and then in the subroutines we can print and have a look at them. And the subroutines can be like, if your entire property is composed of multiple sequences, then even for the intermediate sequence match you can call the subroutine, and thereby giving you a better visibility as to how the property has progressed or why it has failed and what were the values of local variables. So you can gain that visibility using this mechanism. So let's look at an example, and our requirement is that we want to wait for the rise on the signal A, and then after that happens, we want to see that it's asserted consecutively for at least at most for 20 clock cycles. That is what we are trying to check. And the way we have written the property is $rows of A. At that point, we are initializing a local variable x equal to 1, and then subsequently we want A to remain asserted consecutively for 1 to we have put it unbounded here, we can bound it as well. And then but the focus is on how do we use the local variables and as well as display them. So in this parenthesis we are putting a comma separated list where we are using the local variable, we are incrementing the local variable for the every clock A remains asserted consecutively, and then this particular expression along with the corresponding subroutine that we want to call on the match, we have put it in this parenthesis. So now what happens is at every point this matches, it's going to call this $display where we will say C1, and then we are displaying the value of the local variable x, and these are the displays that shows up in the log file. And then at one point of time the signal A goes low, and that is what we are checking over here. After 1 clock delay, after this unbounded sequence, the A must go low, and at that point the value of x should be less than or equal to 20. And along with this expression, again within the parenthesis we are using a comma, we are attaching another system task calling $display C2 equal to, again we are displaying the value of local variable x, and here you can see that C2 x gets displayed to the value 9 up to which it has counted. So this way you can attach subroutines. Here we are showing the the system task for the debug purpose, but you can put other void function calls or the task calls over here, wherein you can do the additional checks, or you can also pass these local variables as an arguments and do some operation on those. We have already seen few examples of how we can pass arguments to the sequence. We will see few more. Here we have a sequence that's checking for some FSM transitions, and we are passing the count for which it needs to stay in certain states, the max number of cycles that it can stay in these states as an argument. And the property, when we invoke the sequence, we are passing the value for that particular argument. So and then here we are using the cover directive on this particular property. And so yeah, here what we need to notice is that we are passing the untyped formal argument. We are not telling the type or the direction. For the arguments we can also provide the type, like for example here we are saying bit type, we can say that, and on the similar lines as stars, we can also provide the direction, like whether it is in out or in out, and then you can also pass like a local arguments, that is also allowed. The default direction for the sequence is always in out, so this way you can restrict, like with input or with output, you can also restrict the type of access that a sequence can have, and this is very useful for making your sequence more useful and more configurable. We have already used some of these sample value functions. Let's look at the total number of options available. So we have this dollar sampled function, which so what happens is, as we know, the action block of our concurrent assertions executes in the reactive region, and there is a possibility that the values used in the assertion, which were from the preponed region, could have changed, and hence the dollar sampled provides the ability to get the values of the signals that are used in the assertion from the preponed region. So when you dollar display them in the error message, you can use a dollar sample to make sure the values displayed are the ones that were used in the assertion, because sometimes this confusion can take place. So when you display any signals in your dollar display for debugging as a part of your action block, you can use the dollar sampled for the signal value, so that you know exactly what was used. And then we have these change detect functions, or like the event detect type of functions, which are rose, fell, stable, and changed. And all of these functions, they essentially utilize the previous sampling events value to decide this. Like a dollar rose returns if the LSB of expression changes from 0 to 1. If you are passing a vector, then it uses only the LSB. And then dollar fell returns if the LSB changed from 1 to 0, and this change 1 to 0 or 0 to 1 is compared to your previous sampled value. Same thing is for the dollar stable. It returns true if the value of expression did not change. Okay, so that in the previous clock tick it was 1, and the current clock tick also it is 1, or it was 0 and 0, so then the stable will hold true, it will return true. And dollar changed is opposite of your dollar stable. It returns true if the expression changed. So in the previous clock tick it was 1, and the current clock tick it is 0, or vice versa, then dollar change will return true. And dollar passed is another useful function. You can pass actually the number of ticks, like how deep you want to look in the history, and then for that specified clock tick, the passed value of the signal that you are passing will be returned. And if you are passing it longer than the history being available, the value 0 will be returned with the dollar passed call. Let's look at some of the examples. So we have here like we are doing an assertion of the property at the pause edge of clock. We are checking if A equal to B, and else is where we are reporting the failure. So we have already seen this. We can say sampled A and B so that it gives us the values of preponed region while this particular statement is executing in the reactive region. And let's say we had built a counter as a part of our verification using Verilog. If I were to write an assertion which would almost replace the scoreboard, here is how I would write it. So we have a sequence s count assert, and count is equal to, we are saying dollar passed of count plus 1. That's a simple incrementing counter, and we are saying over here, we are using it in the property at pause edge of clock. We have this another construct. We'll talk about it when this is a property construct, so we'll talk about it in the context of property. So disable if not of reset, and this means that the property evaluation will be disabled when this condition is true, and this particular statement is treated asynchronously. It's not affected by your sampling event. As soon as this condition becomes true, then your property evaluation is stopped, and even if the property is in progress, the evaluation is stopped when you see the disable if condition becoming true. So while the reset is asserted, these various sequences or the conditions might not hold true, so you can use the disable if and then pass on a condition where you do not want the property to be evaluated. And here we are calling count assert, and then if the reset is not asserted, then this particular sequence will hold true. And then we have just printed some of the values of using the $past, and you can see that they sort of match the expectation, and you can also see that in the waves. Okay, note that these sample value functions that we discussed, they are not limited to only sequence and property. They can be used in your procedural code as well. So you can call this $past, rows, stable, fell. You can also actually pass an explicit clocking event, because when we did it in the properties, the clocking event was clearly mentioned, but you can pass a clocking event as an argument, and if the default clocking event is not specified, you can pass a clocking event and then extract any values that you want in the procedural context as well. And here we are showing, this is actually the always block that was printing in the log file in the previous slide. So you can print, you can use these values. I mean, you can use the sample value functions even in the procedural code in this form, and they would work just fine. And here it's using the always, so based on the context, it's figuring out the clocking event as always passage of clock, but you can pass the clocking event, and you can pass, for example, for the $pass, how many clock cycle before you want to know the value of the variable, that also you can pass. Okay, so this concludes the session on sequence. I know this is the long one, and this is the most tricky one in the case of assertions. Assertions by themselves are tricky, and then we have completed one big chunk of it with this session. So at the beginning of the session, we wanted to learn the sequence, and learning the sequence meant learning the operators. So we learned about delay operator, 3 types of repetition, then throughout, within, intersect, first match. We have learned each one of these operators, and among them the delay, repetition and first match are very important, so make sure you are clear with them. And then we looked at the sampled value functions and how they can be utilized, and how they are useful in both the sequence properties as well as in the behavioral code. We have looked at how to pass arguments to sequence, and how to use the local variables within the sequence. And we have done the combining of sequences to create more complex sequences through composition, where concatenations, and then using and or. So we have done the complex sequence creation, and we have briefly looked at how the debugging of the sequences can be assisted by attaching subroutines to it. In the next session, we will look at more into details of properties, as we have been repeating everything that we have studied in the context of sequences, the sequence operators. We can apply them to properties directly as well, although it is recommended that you compose complex properties using the sequences, but whatever that you have studied in the context of sequences can directly be used within the properties as well. Then there are additional operators that can only be used in the properties. For example, the implication operator that we took a slight detour to study in the context of sequence cannot be used within the sequence. So the validity of sequence, the operators that provide validity to the sequence are part of the properties, and they can only be used in the property. So property operators are applicable only to the property, they cannot be used in the sequence, but all the sequence operators can also be used in the property. So in the next session, we will look more closely into property and the property specific operators. So thank you for listening.